be active in your note taking. That way, you kind of actually understand what's going on. I imagine that quite a few kids are, um, you know, I imagine that quite a few kids are probably just not really paying attention that well, and I want to make sure that we avoid the issue or the problem of having redo all your work or having to watch extra videos. You're here with me right now. Just pay attention, answer the questions, engage with the class, engage with us. That way you can kind of, don't have to redo all your work and have to watch the video twice or three times or four times. Nobody wants to do that. So, right. All right. So, we're gonna go ahead and get started here. I think somebody might have snuck in on me. Yeah. I'm glad to hear that. So, what are we missing here? Boy, going. Nope. All right. Sound like somebody was sneaking in. All right. So, the first thing we're gonna do is kind of go over some notes, and then kind of go from there. So, everybody see the note slide, presentation slides here for today? All right. Cool. So yesterday actually it was yesterday. So we actually went through the questions here. Please make sure you kind of look over the questions in your notes and your recap because these type of questions could definitely show up on the quiz on Friday. So that's what we want to kind of make sure we learning during this process. So again, you have everything you need. You have the notes, you have questions I'm going to ask you, you have the activity. The activity worksheet has questions in it. So make sure you're looking over all that material. All right, so today we're going to actually talk about what is electricity and how electricity works and what's going on. So remember, we were talking about charged particles being positive and negative, and then us humans making the particle do what we want them to do. And that's what the charge launcher was supposed to be about. Can you make that charged particle do a loop? Can you make it bend upward, downward? And if we humans can do that, then we can actually harness the power of electrical charges and create electrical current and create electricity. So the movement of electrical charges is an electric current, which we're going to talk about in a second, and that produces a magnetic field around it. Okay? So all charged particles have fields themselves, but when you put a bunch of them together and they're all moving, that's going to create an even larger magnetic field. Okay, so electricity is a physical phenomenon associated with this motion of matter, and that has electrical charges in it. So various types of phenomenon that electricity, obviously, lightning in the example of electricity, that is a charged particle going from the atmosphere to the ground to discharge to release that energy, and it releases that energy in the form of not only light, but also in the form of heat and movement. Okay, and that movement also creates thunder, which is sound energy that comes from lightning striking. Okay, so those are particles that are in the atmosphere that are essentially building up and they discharge to the ground and very quickly, very hot, very fast, lots of light, lots of sound energy. And yes, people can die from them. Normally, every year, about 20 people in the United States die every year from lightning strikes. So it's not super common. Most people who die from lightning strikes are actually hiding under trees. So during a lightning storm, hiding under trees is actually probably the worst place to go. Don't because lightning wants to strike things that are tall and high, and it can strike the trees. And if you're hiding underneath that tree, that's not a good place to be. So if you are in a lightning storm, the best place to go is inside a building, obviously. And then if you are in an area that is where you can't go inside for whatever reason, you want to lay flat on the ground. That's the best way to avoid being struck by lightning. However, even just standing on the ground or laying on the ground, if the lightning strikes a tree or whatever around you, that lightning can travel through the ground and get you as well. So lightning is kind of a scary thing, but again, not that many people die every year from it. So Static electricity is also an example of current. We're going to take a look at that here in a second. Electric heating, if you have a blanket or something like that, or if you have a furnace in your house, all those run off electricity. Electricity can create heat. Electric discharges, or all kinds of electric discharges. You've probably been shocked every now and then if you touch something like, oh, that's out. There's lots of ways to build up charges. And again, we're going to look at another way here in a second. So electricity is simply the movement of charged particles, and especially in our case, electrons. And so that charged particle can create an energy field that we call a magnetic field. That energy can be used to do work. And so us humans can harness that electricity, and we can actually make it do work for us. And that's how things work. And for electricity, we are harnessing that energy. All right. So for example, here's a quick little example of what static electricity is. Here's John Travolta. He is taking in electrons just like creates a current, which is going to allow the electricity to fly to a metal object. Metal objects love to take on electrons without move. When he does that, the electrons can move, and you get yourself a nice little shock. Rubbing the foot electrons, and then the electrons can actually exit your body and shock you or other people. So the best way to do this is if you have a carpet, you wear wool socks. You can rub your foot on them real hard, real quick, and go around and poke your little brothers, little sisters, and give yourself a nice, a nice little jolt of electricity on that. And it's not that much. It's pretty small. So, all right. So, what is a current? And the current is kind of what we're focusing on and how currents work. So, consider a copper wire. Copper wire has bajillion copper atoms in it. It has a lot of copper atoms. Okay. Now these copper atoms are metal. They have electrons that are floating around. Remember we talked about electrons being on the outside of the atom on Monday. Those electrons are free to go places. Okay, and they oftentimes do, especially in metal. They'll jump. They'll go from atom to atom at will. Okay? However, if us humans can make the electron go from this atom to this atom to this atom to this atom to this atom, we can create basically what's called a type of a chain effect, not a chain reaction, but a chain effect, where when the electron from one atom jump to another one, it has to kick out an electron. Okay, so you can't have too many electrons. So this copper electron could kick out this copper electron, which could kick out this copper electron, which could kick out this copper electron, and these electrons can keep getting kicked out, and that can create a current or a flow. So you see this picture here. This electron can go over here, and then that electron can go over to this one, and essentially they're kicking out electrons along a path, and that creates a chain effect that we call an electric current, which is another word of saying electricity. So the atoms have a certain number of protons and electrons. So if you move one to a different atom, you're going to have to displace an electron and make it move. Now this happened naturally, but it also happened randomly in materials. But again, if we can make it do what we want it to do, then we can make this electric current continuous, or we can make it non-continuous, and we'll talk about that in a second or Friday, and we can create an electric current. Okay, so the flow of electrons from atom to atom to atom to atom is what is called an electric current. So kind of like the flow of water current. The flow of electrons, the flow of electricity is an electric current. Okay. So the direction of a current. So the current is going to be a little bit different than the flow of electron. And so you have to kind of be careful here because the current and the electric field are going to be kind of doing different things. So electricity is the movement of an electron. And so what are the electrons moving towards? They're moving towards protons because electrons are negatively charged, right? So electrons are going to be moving from proton to proton to proton, okay, because opposite charge attracts, okay? However, remember yesterday, Monday, we talked that the field goes away from the electron, right? Away from, or sorry, it goes away from the proton, not towards it. And so the direction of electron is going to be opposite the direction of the field or the current. Okay? Does that make sense? I hope it does. So the electron is moving toward the proton, but the field is not moving toward the proton. The field is moving toward the electron. So as the electron moves, the field goes in the opposite direction. The field doesn't go toward the proton, the field goes backwards. And so the direction of electrons is opposite the direction of the current. So you guys see that going on here in the picture down here at the bottom. So in a battery, for example, the electron will leave the negative source and the electron will go to the positive end of a battery. However, the electricity, the flow current, will go from the positive to the negative. And especially with the battery, you have to connect the positive and negative in order for anything to work. It has to be what we call a closed circuit. So just that highlighted sentence there is really important for the electron flow. Now, how do we know the direction of the field and what's happening? This is really important is in order to kind of figure out, well, how do I make this stuff work for me? And that is called the right hand rule. So everybody put your thumb up on your right hand. Okay. The right hand rule basically is when you close your fingers, you're creating a direction for the current. Okay. So go ahead and do that with me real quick. I know it's weird and funny. But when my thumb is up and I close my hand is moving in a counterclockwise way, right? So go ahead and do that. Your right hand rule. If the direction is down and I close my hand, it is moving in a clockwise. 12, 1, 2, 3, 4, 5, 6, right? Okay, so that's the direction. If the current is, or if the electron current is moving upward, and I close my hand, I go 12, 11, 10, 9, 8, 6, 7, 6. Okay, that's a counterclockwise movement. And this is a clockwise movement. And the reason why we want to do this is kind of figure out how is the electric current, how is the magnetic field working against the current. Okay? And this can allow things to work for us. So we have some letters that we use for abbreviation. I for the electron current, and B is for the magnetic field that it produces. So remember, all charged particles have a field, and when you put them all together, the current, it creates a magnetic field. And that magnetic field can repel, can attract, it can do different things. So that's what we're actually going to practice today. We're actually going to practice a little bit about the right hand rule. Is it moving clockwise, counterclockwise, these fields? How can we change that? And really, the answer is pretty simple for a wire. So a wire can only go one or two ways. It can either go left or right or up or down. It can only go two ways. Okay, so if it's a wire. So for wire, we can basically, so if I have my pencil here, if it's coming towards my face, the magnetic field is going this direction. If it's going away from my face, I'll use my thumb, it's going in the opposite direction. And then, of course, I can put two wires next to each other and they can have different impacts on one another. So today we're going to, there's some additional resources about what is electricity and more about the right hand rule. Again, I encourage you, if you're weird, if Mr. Kane doesn't make any sense, check out the videos, check out the articles, help, learn the material that you can. Of course, and ask questions. So today we're going to take a look at part B of our charged particles and electricity. Again, I'm going to give you guys about 10 minutes, 10, 15 minutes to work on this activity together in breakout groups. Again, when we're in breakout groups, talk to each other, have fun, interact with one another. Again, if people are not really helping or not being productive, if your classmates tell me that, we'll have a conversation about what it means to be a good classmate. Okay. Again, although you are working together, it needs to be your own work. No sharing your work, no copying, no word for word. But again, you guys can put stuff up on the screen. You guys can help each other out. This one is a little bit trickier as far as like, what do I do? What am I trying to do here? And on this. So talk to each other, kind of figure it out. Then, of course, if you have questions, put them in the chat box, and I'll come and visit your breakout groups with you guys. So again, if you go to that worksheet that we did yesterday, let me pop it up here. Let's see. So if you go to that worksheet on your weekly schedule, you will find the activity for today. We're doing part B. So it's the same document we were doing on Monday. Down toward the B, you have another little gizmo. And then on this gizmo, and I made a video on that handout to kind of show you how to do this. So if you need to watch the video, that's fine. But on this here, basically you have a wire, and then you have magnets. And the magnets are going to record the magnetic field going around the wire. Here's your current over here. So you can see the magnetic field is changing when I do different things to my wire. You can also see that the battery, I can flip it. So if I have a negative amps, I'm flipping the direction of the current. If I have a positive amp, I flip that battery upside down. So play around with that. Talk to your classmates, and then again, of course, let me know if you guys need anything. So I'm actually going to stop the recording because it doesn't record breakout groups, and then we'll pick up from there. All right. So. Right, so we just got done with the breakout group where you guys were looking at what happened to a wire and a charge field around a coil. So a real quick couple of questions I want to cover, kind of a recap. So so in your chat box, let's type it up. So how does the strength of the induced field change when you increase the amperage through a wire? So what happened to the field when you increase the amperage through a wire? So let's put it in the chat box.
The compasses start moving counterclockwise more and more the more amps you bring up, right? Is that the correct answer?
What do everybody else think? I got one person.
The field around the wire gets stronger, whether you increase the amps in a positive level and make it counterclockwise, or to a negative level, make it clockwise.
Okay. All right. So when you first start at the very beginning, there's no field at all. But when you increase the amp, kind of note what's happening to the compass. When you increase the current, it's getting stronger and stronger and stronger, right? So go from 0 current, and then the needle moves more and more and more and more as you increase the current. Okay. So as you increase the amp, you're going to increase the field itself. Okay. All right. So how does the strength of the field change when you move away from the wire? So if I were to drag this, what do you think would happen?
Depending on how far out you are, the less likely the compass would be affected by the magnetic field.
And how would you know that, Hannah? What will the compass do eventually?
Eventually, the compass will be attracted back to the north of the other poles.
Perfect. Yep, exactly it. So if I grab this compass, eventually, the further away I get, it will eventually keep going back to the north. Keep pointing back to the north. And notice it takes a little bit of distance for that to happen. Okay, that's because I have a lot of amps running through that wire right now. Okay, but eventually, so it was pointing almost to the south. Further I get, the more north it's going to go back to me. So good, awesome. All right, a couple quick questions here. How do you think the strength of the magnetic field would change if you inserted a second wire through the table going the same direction? What do you think would happen? Think it will get stronger? You think it will get weaker? Think they'll cancel each other out? Everybody should be typing in the chat box. So if I put a second, so if I put a second wire in the same direction, Yeah, so it would get stronger. What if I put a second wire in there, but they go in the opposite direction? But well, one in one direction. One, I mean that is true, Landon. But so if I put two wires and they go in the opposite direction, they might even totally cancel each other out. Like there might be no effect at all, and that does happen. I want to talk a little more about that next week. Yeah. All right. Electric wires in your home carry a current that changes direction about 60 times per second. How will this affect the magnetic field around these wires? And that is true. The wires in your home are carrying a current that's changing direction. So about 60 seconds a minute, they're doing this. And I'm not fast enough to do that. But they're doing 60 seconds, or 60 minutes, or 60 times a second. They are flip flopping the current. We call that 60 hertz. So what would happen to the magnetic field if I flip flop? Yeah, so the magnetic field is also changing every 60 times a second. The easiest way to tell that this is happening is if you take a video camera and you look at a light, you'll see that your light actually flickers. Now our eyeballs can't see it, the light flickering, but the light is flickering 60 times a second. And your cameras can pick that up really easy, like on your phone and stuff like that. So if your cameras are flickering, your light, like, oh, what's going on with the light? They are flickering 60 times a second. So they look like they're on all the time for us. But that's actually how electric current works in your house, is that it is flipping 60 times a second or more, depending on what type of wires you have in your house. All right, that's technically in the class time, but the last thing I want to say real quick is on Friday, we have a quiz. We still have some notes that we're going to cover, and then we're going to take a quiz. So I encourage everyone to look at all the notes before Friday. And then on Friday, we'll just do a refresher and take the quiz. Because it's not always fun to learn something brand new and then take a quiz about it. Okay. So you have, I think, 7 more slides that talk about type of electricity that humans produce. Kind of interesting slides as well. So review all the rest of the slides that you already have. You already have everything you need. And then we're going to take a quiz on Friday, and then that'll be it. All your work is due on Friday, but tomorrow we're just going to focus on the second part of that professional habit skill tomorrow, and then get ready for the quiz on Friday. So, if you guys have any questions, as always, make sure to reach out and contact me, okay? All right. See you guys later.